with you about a few things. I don't have an outline slide, which we always tell our students the first thing you have to do is have an outline slide. Well, I didn't prepare one because I had too many slides to begin with. But what I'm going to talk to you a little bit about is something about me, my background, because of course it's our backgrounds that more or less help decide the paths we take when we get into education, especially STEM education. I'll talk a little bit about environmental engineering because that's really what I am. I'm an environmental engineer, although I wear different hats. Sometimes people think I'm a geologist, sometimes people think I'm other things, a chemist, for example. But what I really want to talk, I guess, mostly about is a new initiative that I've recently gotten involved with STEM outreach at Clemson University. So one of the things I'll do is tell you a little bit about that, but also I would also appreciate feedback from you. Since you guys are sort of in the trenches, I guess, the way I'm in the trenches at the university level. So the department I'm in has a very unusual name. It's the Department of Environmental Engineering and Earth Sciences. We have many different degree programs, both at the undergraduate level and graduate level, including environmental engineering, biosystems engineering. Those are our two ABET accredited degrees. So if you're going to want to become a professional engineer, this would be the first step, is to get those ABET accredited degrees. We also have an undergraduate degree in geological sciences, which I actually am the undergraduate program coordinator for. And we have a minor degree program in environmental science and policy. So sort of the recurring thing is a lot of environmental activities going on, science, engineering predominantly, although we do touch on policy a little bit. I'm also a faculty member in the graduate program of environmental toxicology, which I'm not a toxicologist, I'm not really a biologist, but it gives me a chance to talk to those people because a lot of the problems we try to solve require multidisciplinary approaches. And when I first came to Clemson, I had an appointment in the experiment station, which is more commonly referred to as the agricultural experiment station. But the financial crisis of whatever, 2008, 2009 sort of put an end to that. Although I still do most of my collaborations with the agricultural people, so go figure. But a little bit about me. So my background, my training, I grew up on a small farm in northeastern part of Nebraska. So I'm a corn husker, I guess, although when I was an undergrad, I never really went to football games. I went to a small country school for the first 8.5 years, K through 8. It was a one-room country schoolhouse. So it's not quite like out of Little House on the Prairie, but sort of like that. So you can imagine the learning environment I had early on for my education very different from what goes on nowadays. One teacher had to teach all subjects, had to teach everything from kindergarten through 8th grade. Went to high school, also a relatively small high school. I think we had about 50 kids in our class. Again, very different experience. My daughter is a freshman right now at D.W. Daniel. I think she says she has maybe 200 kids in her class, or 150 or something like that. It's just like, whoa. We had 50 people in our class and maybe 200 total in junior high school and high school together. Obviously, I did stay on the farm. I didn't see the future in that. I also, somewhere along the way, got interested in science. And that was sort of unusual in the sense that I didn't know any scientists growing up. I knew farmers. I knew some other people, grocery store operators. But one of the things I did know, obviously, I had to wear glasses, so I knew an optometrist. So when I started thinking about careers, and they talked to you about careers in high school, one of the things that came to my mind is, well, maybe I should try to be an optometrist. That was something I had seen, I had known. I didn't know any engineers, I didn't know any scientists. How would I have even thought of a career in that field? So I guess that's one of the points that I'll probably mention more than once is if we want children, no matter what age, K through 8, middle school, high school, if we want them to become more aware of opportunities in think we need better role models. So that's one of the things that, and I'm sure you all know that as well. So I went to this very small college in western Nebraska, and I was going to go into pre-optometry, and I had to take a lot of biology, and I realized I didn't really like biology that much. It was way too much memorization for me, for my tastes. Don't want to offend any biologists. But, you know, looking back, it was very, very good that I had some of that biology, because now I can talk to the environmental toxicologists the way most engineers cannot. So I guess that's the second point is the paths we take, the paths we should talk to our children or our students about. It doesn't have to be a linear path. It can be a very curved path sometimes. So that's another point, a recurring theme. I decided when I wasn't going to be an optometrist anymore, I decided to go into engineering. I decided on chemical engineering because I sort of liked chemistry. I had a really excellent chemistry and physics teacher in high school. Again, role models. But after 5 years of college, I lost a year when I transferred. I decided I had enough of college. I needed to work, I needed to make money. And so I was a real engineer for 2 years. And didn't really like it. I didn't feel challenged, mostly. And so then I decided maybe it's time to go back to grad school, and I had always wanted to do environmental things. And so I ended up on the West Coast. This gave me actually an opportunity to get out of Nebraska. I was tired of the cold winters up there. So I got to the West Coast and got sort of into that pipeline where you get a master's degree, and the next thing you know, you're getting a PhD, and the next thing you know, you're doing a postdoc somewhere that, you know, which I did at the University of Michigan. So anyway, that's just a little bit about me. Some kid off the farm in Nebraska ends up on the West Coast at one of the best universities, the best institutes in the country, in the world for that matter, and even at the University of Michigan, another outstanding institution. And now I'm at Clemson University, another outstanding. You know, it's like I'm gee whiz, look at me, you know. I was able to do it. I don't know how, but it happened. So again, I took some time off, so I was an engineer at an electronics company in Nebraska. After my postdoc at Michigan, I was in Texas for a while with my wife. None of us we didn't really like Texas that much. And so we were very happy to come to Clemson when we had the opportunity. My wife is originally from South Carolina. I met her in California, go figure. It's not like I was going to come to South Carolina and she wasn't about to go to Nebraska, so we met in California. So anyway, when I first came to Clemson, I was not in environmental engineering. I was actually hired in agricultural and biological engineering because of my ability to, you know, relate to lots of things that they were interested in, including things like non-point source pollution. And then, again, there was some reorganization going on about 15 years ago, and so that prompted me to go to the School of the Environment. And since then, I've been at Clemson now longer than I ever expected. But not 35 years like I was eavesdropping and heard some people talking. These are just some examples of the class I've taught since I've been at Clemson and also at Texas A&M. And again, I don't want to overwhelm you, but if you pick out some words, you'll see things like chemistry. I like chemistry. I do a little bit of geology, and I've sort of taught myself how to do some other things. Statistics, I've gotten better at. What I'm really teaching mostly now are things like hazardous waste management, which means like working with those really nasty chemicals that we're all afraid of. I also do Introduction to Environmental Engineering, which is a broad overview class, and the water wastewater treatment class, and design. I do a lot of design. So I used to teach class on problem solving, but now I more or less do problem solving through every class I teach. Because that's sort of what engineers, we pride ourselves on our ability to solve problems. Okay. Sometimes we cause problems and then we have more problems than we try to solve, but that's okay. We usually look at the other engineering disciplines and say they're causing the problems, so we can come fix them. Okay, and again, I'm not really going to talk about my research other than to say it's been very fun working with grad students, but I'm actually working a lot more with undergrad students nowadays, doing things like creative inquiry, which is really big at Clemson. And I work with other people, collaborate a lot, which again is fun. If we're trying to really solve problems, we can't know everything. And so I work with the biology types. I work with policy people. We all sort of bring different things to the table. So that's actually one of the shortcomings that we have at the university nowadays in our education is we're so highly focused on the technical aspects that we don't let our students have enough interactions with other programs, especially the non-technical programs. So, and that's hard because it's almost like a different language sometimes. I've been trying to work more and more with the education people on campus, and that really is a foreign language from my perspective. We're not trained in education, as you know that. Can you believe that? We're college professors, and we never had a class on how to teach a class. It's very interesting, very different idea. So anyway, for the people who like math, you probably know about Venn diagrams, and so this is sort of just where I like to be. I sort of like that middle part. Sometimes I can cover multiple circles, but a lot of times I'm working with other people to solve those problems. Okay. Now, how many people know what environmental engineering is? Because if a lot of people know environmental engineering, I'm going to go through these really, really fast. You guys know? Okay, so I'm not going to dwell on this because I really want to get to the fun stuff, the design challenges we're doing. But essentially, we're trying to protect public health, and we do it in a variety of ways. We provide safe drinking water, clean up wastewater, and things like that. The thing that we're always looking for are contaminants or compounds, chemicals oftentimes that can hurt people or at least cause adverse health effects. We have different scales that we work on, different time frames that we work on. Being in a geology department, we have geologists who think on geologic time scales. I have a hard time wrapping my head around some of those time scales. I tend to work in much shorter time scales. But it's important to know a lot of these. We also do a lot of Earth systems work. So a lot of our really pressing environmental problems nowadays are not things that a single person can clean up because they're distributed kinds of problems. For example, global warming or at least climate change, if you want to call it that, because there's a lot more to it than simply the Earth heating up. We also have ocean acidification going on and sea level rises and that sort of thing. Stratospheric ozone layer, that was probably one of the success stories, at least in some sense, that they were able to cut down on the use of CFCs, chlorofluorocarbons, and now the ozone layer is probably slowly recovering, but it's going to take time. One of the things also environmental engineers we talk about is, doctors save lives, right? Well, I've seen figures, and again, I'm probably biased numbers, but people have said that environmental engineers, environmental scientists have saved as many lives as doctors. And it's mostly when we think of providing safe drinking water. And in a country like the United States, we take it for granted that we have safe drinking water. And if we look at the numbers worldwide, 4 billion people don't have access to healthy drinking water, safe drinking water, or they lack access to sanitation. Have you heard of the acronym WASH? Water, Sanitation, and Health. It's really big if you're working in developing countries, which I'll mention a little bit later. I'm the faculty advisor for the Engineers Without Borders. And so we have some projects overseas that we try to help people in developing countries. So again, safe drinking water. Somebody know Spanish? Essentially that sign on the left says don't drink the water. You don't have to read Spanish, you can get that from the signage luckily. Down in the bottom right, that's what we would like to have. The fellow up there drinking water I really wouldn't want to drink. I wouldn't have to. But sometimes they have no choices. Okay. Wastewater treatment, this is essentially cleaning up the water before it returns to the environment. Air quality, we work in all phases, if you will, all environmental compartments. So we do air stuff. Solid waste disposal, this is again a big problem. We kind of live in a throwaway society. lots and lots of solid waste every Thursday. The truck comes and picks up the stuff, and it's like, whoa, isn't that great? There it goes, and we don't have to worry about it anymore. Well, somebody does have to worry about it, and that's the people who deal with solid waste. And it wasn't that long ago, probably 10, 15 years, that we thought we were going to run out of landfill capacity in the United States. And things have changed a little bit. We've gotten a little bit better with the engineering of these systems. But it's still a problem, likely to be in the future. We sit in front of computers sometimes. I started out actually wanting to be a modeler, and then I realized that wasn't much fun. I'd rather be in the laboratory. But we have some people that do computational modeling of various types. I do a little bit when I have to. Sort of the new big thing that we do is sustainability. We are, among the different engineering disciplines, we're probably uniquely poised to be the ones to lead the sustainability effects, because we've been doing it as long as people have defined environmental engineering. So we do things like life cycle assessment, which in my mind is really nothing more than a mass balance, material balance, following the flow. So if you're a good bookkeeper, a good accountant, you probably would enjoy life cycle assessment, except for the fact that it's data poor. It's hard to get your hands on good data. And we do some other things. Energy is a big topic now, so we have some folks in our department working with biofuels. And we're actually one of the few departments of environmental engineering that have some nuclear folks in the program, so that's also somewhat interesting. The kinds of classes, so again, if we were looking ahead, if you're advising high school students or even middle school students, these are the kinds of classes that you would take if you were going into a bachelor's degree program in environmental engineering. So lots of science, chemistry, physics, biology, lots of math, 4 semesters at minimum, plus statistics. And if you could take something like linear algebra, all the better. Computer programming, computer-aided design. These are the things that environmental engineers take, and frankly, just about any engineering program would be taking these, except, they would trade off some. We probably have more chemistry than any other engineering discipline other than, say, chemical engineering. And of course, earth science is important too, because we work with the planet. Again, just different things. So this is more or less, we have courses that link back to the pictures I sold, so I'm not going to dwell on that. Our students do have a variety of job opportunities. They go into consulting, sometimes they go into government or industry, or they go to grad school and get some more education. So the jobs are out there. The demand, as you know, it's STEM, has a big demand. Environmental engineering is no different. We're not one of the biggest engineering disciplines by any stretch of the imagination. That would be civil, mechanical, sort of the more traditional programs. But we're about the same size as some of the other ones that are kind of up and coming in the sense of chemical engineering and materials and biomedical. And we're also one of the specialty areas if you're going to become a professional engineer. And this is just something I pulled off the Bureau of Labor Statistics just a couple days ago. So we are up there, and the salaries are not bad. Sometimes when we hear what our students make, it makes me wonder why I'm a professor. I should get a job. I mentioned that I'm the faculty advisor for Engineers Without Borders, and so again, this is a good match for me because of the shortage of clean drinking water around the world and sanitation issues. We don't always do environmental things, but that seems to be one of the big things we do around the world. We've had projects in Gambia, so about a year ago I was in Gambia, which is in West Africa. We have an ongoing project in Nicaragua. We used to be in Liberia, also in West Africa. So we usually try to have one project going in Central America and one in Africa. And it's a great experience for the college kids. They get to visit an exotic, if you will, like its location, learn some culture, but they also get some hands-on experience with engineering and science. So we actually have them do some designs and again, I'll skip over this. This is just, a lot of times we arrive at places that other aid groups have been to before. And so sometimes, again, we're sort of cleaning up the mess. Not everybody knows what they're doing, and so sometimes we find wells that have failed, pumps that have failed, and it gets to be a challenge sometimes. Our trip back in May to Gambia, we were probably the fourth or fifth group of people who had come to try to help this community, and so we were looking at things from China, from Taiwan, from who knows what, of course, all in different characters, languages. We had a rototiller we never could get running because I couldn't read Chinese, and there was no instruction booklet. Okay, but this is really what I want to talk about, and hopefully this is where you might have some interest. And this is a program that's been going on at Clemson now for about 5 years, and I've only been involved less than a year, and so I'm still learning a lot about what this is. But it's a program, it's an outreach program in the College of Engineering and Science where we try to have activities, tours, design challenges, all with the intention of getting people more interested in STEM. And of course now we bring the art in it, so it's STEAM. I'm sure you've heard of that term too. So this is the mission of the Imagine program. But essentially we're trying to get more people interested in STEM careers. And again, that can be hard if a lot of the kids don't have role models, if they've never ever known an engineer or a scientist. It's hard for them to even realize what these careers are. Are any people guidance counselors here? Okay, so I can say a couple. I'm not sure our guidance counselors know what these kinds of jobs are. The guidance counselor I had in high school, he didn't know anything about STEM careers. Of course, they didn't have that term back then. But, so I think we need to do a better job, not just with the children and the parents and the teachers, but also the guidance counselors. Because if we don't make everyone aware of these opportunities, then it's hard to find out on their own. I sort of feel I'm lucky. I kind of stumbled backwards into it, if you will. I just knew I couldn't be a farmer, so I sort of fell into something else. So these are just, I pulled up one slide of some of the places that we've been this semester. I don't have January on there, but some of the places we've been, some of the places we're expecting to go to. Not everybody goes to all events. This is sort of volunteer activities on our part. But just a couple weeks ago, we were going, for example, the design challenge tour, and I'll talk a little bit about that. Has anybody been at an Imagine program? See, that's just not right. You know, it's so close. Why aren't we working with you guys? I don't know. We need to, because we need to hear from you what works and what doesn't work. And you probably, well, maybe you don't need to hear from us, but we would like to think you need to hear from us. So the Roadshow, one of the typical things we do is it's sort of a Friday night, Saturday thing. And this is what we did in Orangeburg. So we drove down, and we have a reception on Friday night, just sort of informal gathering, talk to some high school juniors, sometimes seniors. Sometimes we get some little kids, school kids that show up. And essentially we just talk a little bit. Some of the college kids come and talk about their experiences, which again, can be some of those role models that we're looking for. And then on Saturday, we get up early, and then we have some design challenges, and I'll talk to you a little bit about that. What we try to do when we do these road shows or design challenges is we link it back to real-world problems. The National Academy of Engineering is this august body in Washington. It's all the top engineers in the country. And over time, they have essentially put together a list of what they consider to be the grand challenges facing the world, for that matter, not just the country. And so what we try to do is we try to sort of cherry pick some of the ones that we think we can do in our design challenges. Obviously, we can't do all of them. I'm not going to try to get somebody to reverse engineer the brain when I can't do it myself. So we stick to the things we know, which again are mostly sort of environmental related, some civil related, and we try to emphasize concepts that they may have already been accustomed to seeing or aren't too challenging. So we talk a little bit about chemistry sometimes. We talk a little bit about physics, things like that. So for example, from that very complicated list, these are some of the types of design challenges we've done. So we have a water, instead of filtration, it should be really purification, but so we try to clean up some water. We do some straw rockets and have a competition with that, build a platform structure, some other things, comet landings. We've done some robotics in the past. The other Imagine people have done some robotics. So it sort of depends who shows up that particular weekend and the activity. But one of the things we've been trying to do more recently is to get away from some of the gee whiz stuff, the very expensive stuff, and sort of get back to the idea that you don't need a lot of expensive things to be an engineer. You know, we can try to make do with some very simple, low-cost things, okay? And so that's sort of the focus that we've been doing. And I'll actually show you some of the things that we do here in a minute. There's some other ideas that we're kicking around, and one of them that I really like is that bottom one, sort of the things that you can do with your kids. This would be, again, trying to come up with some ideas and perhaps some items that are readily available around the house. And these would be things that parents can do with their kids, because again, if the parents aren't involved, how do we expect the kids to be involved? So we need to do that. Okay, so in Orangeburg, these are some of the slides that Dr. Brad Putnam, who's our Imagine coordinator, showed. So I'm just essentially going to, I stole this slide, I'm going to show some of the slides he did. There's one or two that we don't show, but these also are some of the activities. So here's some of the robotic stuff. But when we had more electrical engineers doing the road shows, they had some things. This is where essentially you got something that looks like a train and it follows along the track, and I can't really see what some of those other ones are, but we'll see some better pictures in a minute. So we live in the world of word clouds, right? So every time you look at something, there has to be a word cloud. So we have our own word cloud. And these are some of the words that have actually come back on our feedback forms from the kids. And so it's important to have these fun. It's important to get them excited about it, to let them know that they can also be engineers, at least in some sense of the word. Because they can follow the same algorithm that we follow as engineers. So that's our word cloud. Okay, so what do engineers do? We use science and math to solve problems. Okay, and the sciences that we often use are, again, chemistry, physics, biology, earth science, and then other people, if you're in the biomedical engineering field, you would use some human anatomy sorts of understanding. But we're trying to solve problems, and so that really gets back to the idea that if we're problem solvers, I think we get some buy-in right away. Okay, I mentioned my daughter's ninth grade at D.W. Daniel. We actually had her not in public school early on. We went to the Montessori school in Clemson, and one of the things we liked about the Montessori school, it was very much hands-on, and so I think because she didn't grow up on a farm, I did my hands-on, whacking my finger with a hammer, that kind of stuff, putting a nail through my toe. I did that on the farm. She didn't have an opportunity to do all that, so we thought the Montessori hands-on education would be the next best thing. And I left with all my limbs, so that's a good thing, and so did she. These are all the different kinds of engineering, at least at Clemson. There would be perhaps some other ones. So we try to demonstrate that some of the concepts are not simply environmental engineering. It's not simply civil engineering. The problem-solving skills that we use and we want the kids to learn transcend all of these. Okay, This is one of my favorite slides. This is what we commonly think of as the engineering design process. Okay, now, there's a couple mistakes with it. For one thing, it looks like it's a linear process. Okay, it's definitely not linear. If we had lots of feedback loops going on, it would be too messy though. Okay, but the idea is we have to identify the problems, and I tell all my engineering students, sometimes that is the hardest thing, is we're working with somebody and they think they know what they want us to do, but sometimes they don't. And so oftentimes we have to ask questions until we really understand what the problem is. And I do this, I'm on the phone sometimes with consultants and they want me to help them with some cleanup sites. And it's like, okay, what is the problem? What do you really want from me that you can't do yourself? Brainstorming the ideas, okay? This is the creative part of engineering. And that is the part that most people think engineers do not have, or any creative skills. Well, maybe we do, maybe we don't, because we also rely a lot on tradition. It's a very conservative field. We know what works. And so for us to stop doing something that we know works, it's going to have to take some momentum to push us off and look at some new things. But brainstorming ideas is very important. Plan the solution, build and test the prototype, improve the solution. At many steps along here, there's going to be feedback where we may be all the way down here and we've built and tested a prototype only to find out we weren't solving the right problem because we didn't understand it. So we have to come back and start over. Right? Now, the reason I like this though, so it's simple, it's only 5 steps. I sort of like things that are either 4 or 5. I can't remember much beyond that. It reminds me a lot of what we learned as the scientific method. Okay? And that's one of the things I like. The scientific method, usually we boil it down to 4. That's okay. And the scientific method relates to something else I like, which is, how many people are in physics here? Anybody? Have you ever heard of Kolya? He's got a 4-step problem-solving method. I love that too. All of these things look alike. Okay? I have some handouts. I should have mentioned that earlier. When we go on these design challenges, we often not just let the kids play, but we try to get them to plan what they're going to do. Okay? So, and I brought enough, I think, for everybody. So if you were to sort of pass them around, that's fine. I'm not necessarily going to refer to them that much. But what you'll see on that page that we have the children do is we first have them try to identify the problem, whatever that problem is. Brainstorm ideas, draw pictures, plan the solution, do some trial testing, all of those sorts of things. And then, ultimately, they have to do something. They have to come up with a deliverable. And that deliverable may be something that can make some yucky water less yucky, or it may be a rocket that's going to go further and more accurately than some other team, or it may be a platform that can take a higher load, put more weight on it before it collapses. Or I've been at some other things where we simply had kids, elementary kids, build rafts, and we start putting pebbles on it to see how many. And I like that idea of competition. I think sometimes we have to be a little bit careful because some children don't always like competition. So again, we have to be a little bit careful. And that's probably where you guys would be much more knowledgeable about, how much should we encourage competition versus collaboration, or is there ways that we can actually do that together, collaboratively compete? Okay, so these were the 3 that we did in Orangeburg. And so let me just show you what some of the things are. I actually was with the water purification, so I'll do that one last. But this is all we brought. Okay, so this would have been the rocket one. So we had the children. We give them all of this very expensive stuff: paper clips, straws, paper, rubber bands, and their challenge is to make this into a rocket that you can blow off the straw. Okay. Now, we don't always tell them right away that you can blow it off the straw. Sometimes we let them think about that a while. Okay? That's the other part that's very important, is to be roaming around, providing feedback, talking, listening to their ideas. But this is stuff that you can find just about anywhere. find this all over my daughter's bedroom floor. And this is essentially similar kinds of things, straws, some Dixie cups, a little bit of yarn. We always bring scissors, of course. They have scissors and tape. As you can imagine, they really like the tape, get a lot of mileage out of the tape. And these are some of the supplies that we bring for the water purification. So coffee filters, that would be what most everybody would want to use. Again, Dixie cups, some bottles that they can cut or use in some other way, paper towels, some batting, some netting, some cotton balls, a spoon. We also give them a large plastic cup with some gravel in it, and a large plastic cup with some sand in it. And again, they have scissors and tape. And we make up the nasty foul water. Of course, we don't really use contaminated water. We use water that we put some tea in, a little bit of vegetable oil, and then either some clay or sand, because we can't work with really hazardous materials, okay? But frankly, those are all model materials that we use in our real laboratory systems. You know, so the tea is a lot like the water when you go down to the southern part of the state. They have all those interesting waters, the brown waters or the yellow waters or the black rivers, that kind of thing. So these materials are not expensive at all. Okay? And that was sort of, again, where we're trying to use, because if we had very expensive things, yeah, it would be so much fun, and maybe we could do better, but I think we can do plenty fine with what we have. Now, this slide we don't actually show the children, so this is sort of something we hold back. But this is sort of a few more words about what they're trying to do. And sometimes we change things up a little bit, depending on who's there, what ideas they have, and so forth and so on. So, for example, for the water filter one, we've more recently been looking at who can produce the cleanest water, but also who can provide the most water back, and that's a valuable lesson. The shortest amount of time, we give all the teams the same amount of time usually. And it's never enough time, obviously, because they could use a lot more. And this is a slide sometimes we show, sometimes we don't show. But the idea, and this sort of goes back to the fact that things are not linear. It's okay to make mistakes. We often learn more from our mistakes than from our successes. You know, many ways to get to the destination. And I think if you're anything like me, my career path has been anything but linear. It's been anything but planned in many cases. But there has been the passion. Okay, so we have to find that passion, I think, in our children, so that we know what gets their attention, what gets them excited. And then if they have the passion and they're willing to put in the effort, really they can do anything they want. Within reason. I mean, I wanted to be an NBA star. That didn't get me anywhere. Okay, so here's just some pictures. This is from Orangeburg. This is the water purification. This is by far the messiest design challenge we do. It takes me about an hour to clean up afterwards. But we have the plastic bin that we try to get them to do most of their messy activities in. We have teams of 3, usually 4 students working together. And as best we can, we always have parents or teachers that come and help us with some volunteers. So we try to roam through, talk to the students. What are you thinking? What ideas do you have? And we allow them to ask questions just so they get better understanding. And I don't know if you can see it from the back, but again, these are just some, they're talking, they're writing, they're planning, they're telling me what they're interested in. The bottom right one, these are what some of our treated water looked like when everything was said and done. And sometimes I feel kind of bad because the sand we gave them, they like to use sand because they inherently think sand is going to filter for them. The problem is the sand we gave them hadn't been washed. So when they would use that sand, their water would actually come up dirtier looking than when it started. Okay? But we told them, again, they had unlimited use of the sinks. They could wash the sand and clean it. But so if you can see these colors clearly, this is the clearest one. Okay, this is one that they did with sand, and it actually looks worse. This is one group that they ran out of all their supplies during the testing, and so all they did is turned in the nasty water I gave them to begin with. So it's innovative, but they also had the most water left. So what we were trying to do in this particular design challenge is get them to test things. Will this material be better or worse for the thing that was in the water? We don't expect them to get it right. That's not the purpose. We expect them to test and observe and correct and brainstorm. So those are the things we're looking for. The one reason I sort of like this picture is this is the cleanest, but it was also the least amount of water that they could generate. And that is a fact of life for us when we're cleaning water. We can provide a lot of dirty water, or we can provide a little clean water. We can't do both always. Okay? We would like to, but we can't always do it. This is the platform design challenge that was going on at the same time. And again, what they're trying to do is build a structure. It's got to have a certain height, and then it has to be able to handle a certain load before it collapses. So this is kind of a civil engineering sort of project. And then this would be some pictures from the rocket challenge. And again, the part that the kids like the best is over here, where they actually get to test their rockets. And so we test it for how far it goes, and we test it for accuracy. And so if you were going to tell a child at what angle should they hold their straw when they're blowing, what would you tell them?
45.
The magic angle, 45, because it's going to go the furthest. Okay? It's got the right balance. Physics, that's elementary physics. Okay, so again, I don't know if you care much about environmental engineering, but if you do, there's a really neat video that a group of students from the University of Maryland, Baltimore County put together explaining what environmental engineering is, and so you could look at that. If you're interested in this program we have at Clemson, Imagine Your Future, that's our website. And a year ago, we were also in Spartanburg, and we did a video. And one of the things I like about that video is, yeah, it has the obligatory professor talking, but what's better is we have a college student talking who happened to be a woman. And that's one of the things we're always looking for, is trying to get more diversity in the sciences, especially the engineering fields. We had some parents that were willing to be recorded, and some children who were there. And so that is sort of the perfect thing, in my opinion. Okay, and that's it. I think that's all I have. The handout that you may have, again, let me grab one just to make sure. If you were to look at the first 3 pages, they all look very similar except for the title. So in all cases, what we're trying to do is the problem definition, understand the problem, trying to get them to sketch out what they would use. So it's really following that those circles that I talked about. On the 4th page, actually the last 2 pages, are these problem-solving steps by Hoya. This is not something that we hand out to the kids, but this is something I hand out every semester in every class I teach. Just because oftentimes people, not just students, but sometimes professors, forget that we can follow a protocol if we're facing a problem that we've never seen before. And again, it starts off with understanding the problem, devise a plan, try it, come up with something. One of my favorite things is when you're trying to solve a problem on the first page of that Hoya is, look for a pattern, draw a picture. Sometimes we simply guess, and then we check our guesses. We call that trial and error or solving by iteration, but it's really guessing. The last one, be ingenious. I tell my students every semester, be ingenious, whatever that means. I need to tell myself that too, just because sometimes, again, we get kind of set in our ways. Okay, so I'm going to stop talking. I'd be happy to answer answer any questions or hear from you about your experiences with trying to get children involved in STEM, especially engineering.